Welcome back. Well, in the last video, we came to the conclusion that we could figure out the volume when we rotate a function about the x-axis. So let's apply that to an actual exercise. And what I'm going to do is I'm going to erase everything because I don't want you to memorize this. Because frankly, I haven't memorized this, and if you do, you'll forget it one day, and then you won't know how to do it. But if you understand why it works, then you'll never forget, as long as you remember basic integration. So let's see. Maybe you want to memorize it if your teacher tends to give you tests that require that don't have much extra time in them, so that just to speed up the process. But you should know what's going on. So let me draw the axes again. That's my y-axis. That's my x-axis. And so since our first example was y equals square root of x, let's stick with that. And for reasons that might become apparent, that tends to be one of the more typical examples when you rotate things around axes. So let me see if I could draw it as well as I drew it last time. Oh, almost. Okay, so that's y equals square root of x. It's not just f of x this time. I've defined it. This is the x-axis. That's the y-axis. And I'm going to rotate this around the x-axis again. So I'm going to get a sideways looking cup thing. And let's say I want to figure out the volume of that cup between the points 0 and, to make it simple, let's just say at the points 0 and 1. Right? So essentially, we're just going to get a cup. A sideways cup is going to look something like this. Let me do a better color. It's going to look something like this. That's going to be the, no, that's a horrible. The opening of the cup. Actually, why don't I use the circle tool? Something, it just dawned on me that I had a circle tool. So the opening of the cup will look like that. And then, actually, I could draw it right here. This would be the opening of the cup. Well, let me do. As you can see, sometimes my videos are a little unplanned. There you go. So that would be the opening of the cup. As we wrote, this is excellent. This tool is very well suited for what I'm doing here. Right? We're rotating around that way. We're turning that function. So the cup's going to look like that. So the bottom part of the cup's going to look like this. And it's solid, so we want the volume of the whole thing. In future videos, I'm going to show you actually how to figure out the surface area of the cup, which I find in some ways more interesting. So how do we think about that again? Let's just rederive it, but this time we'll use a specific equation. So we just have to figure out what is the volume of one disk and then sum up all the disks. So let's say this disk right here. This disk. Actually, let's just take this disk at the endpoint right here that I've already drawn something for. So what's the radius of this disk? The radius of that disk is f of x at that point. Well, f of x at that point is just square root of x, right? So let me just write that. Radius is equal to square root of x. And of course, and so the area of that disk, the area is going to equal pi r squared. Well, the radius is square root of x, so it equals pi times square root of x squared. So it equals pi times x. Right? That's the area of each disk. And then if we want the volume, we just have to multiply the area of that surface times the depth of the disk. Right? So I'm just trying to show, you can imagine this is kind of like a quarter, and this is the side of the quarter. Right? And we saw in the last video that depth, that's just a very small change in x, because we want to get these we want each disk to be infinitesimally thin. So the width is just dx, right, at any point. The width is dx. So the volume of each disk, is equal to the area, which we just figured out was pi x times the depth times dx. That's the volume of each disk. So the total volume, we'll just call that total, is going to be equal to the sum of all of these disks. That was one disk I drew, then you're going to have another one here, you're going to have another one here, another one here. You're going to have infinitely many, and you want them to be super, super, super thin so that you get an accurate measure of the exact volume of this curve. Otherwise, it would just be an approximation, and that's where we use the integral. So it'll be the integral from, and my original boundaries were 0 to 1. Right? You know, the disk we use as an example, this is probably, this is the last disk. So this one will actually have a radius of 1 of the square root of 1, which is 1, right? So let's see what not that you have to know that, I'm just trying to keep emphasizing the visualization. So what will be the integral? Well, we're going to go from 0 to 1. And we're going to sum up a bunch of these disks, which we've already defined. So it's pi x dx. This is looking to be a fairly straightforward integral. So what's the integral of that? Well, that equals pi is just a constant, and the antiderivative of x is x to the 1/2 over. I'm sorry, x. It's x squared over 2, right? I don't know. I've been a little rusty since I last did some antiderivatives, but so we get x squared, we get pi times x squared over 2, right? That's the antiderivative of that, and then we have to evaluate it at 1, and then subtract it, evaluate it at 0. And so what do we have? We get 1/2 pi, so we get pi over 2, minus 0/2 pi, minus 0. So it equals pi over 2. There we go. We just figured out the volume of this cup from 0 to 1. Reasonably interesting. Let's see if we can do that again to figure out just to give you another example, just to hit the point home. To see if we can figure out the volume of a sphere, the equation for the volume of a sphere. So what's the equation for a circle? It's x squared plus y squared is equal to, say, r squared, right? And let's write that in terms of y as a function of x, just so we have something that we can work with the way we learned it. So we get y squared is equal to r squared minus x squared. And then we get y is equal to the square root of r squared minus x squared. Actually, now that I realize it, I'm going to not do this because I think I think I'm going into too complicated of a problem. I did that on a fly. But I will, in the next video, I will do slightly more complicated without going to this one because I probably don't have time for it. I just realized. Anyway, I'll see you in the next video.